In this lesson, we'll look at redox chemistry. At the end of this set of slides, you should be able to state the simultaneous nature of reducing and oxidation reactions, which means that when a reaction has a reduction, there must also be an oxidation. So redox actually means reduction and oxidation. Both of these must occur together. Now, there are many definitions for reduction and oxidation. This is based on history. So the first one we had was, of course, the loss of gain of oxygen. That was the first one. The second one we went in history was the loss and gain of hydrogen. And then after that, we go to the third one and fourth one. So first, let's look at the original definition. This is not very useful definition, but it is based on history. So oxidation was defined as a gain of oxygen. That's how the word came about, oxidation, gain of oxygen. And reduction was taken to mean the loss of oxygen. So in this case, since zinc gained oxygen, it was oxidized. Since copper oxide lost oxygen, it was reduced. The next one that we went through after that time was on hydrogen. Now, hydrogen was taken to be the opposite of oxygen. Hydrogen and oxygen was very important because it was part of water. So in this case, we see oxidation is the loss of hydrogen or the gain of oxygen, and therefore the reduction is the gain of hydrogen or the loss of oxygen. So in this case, sulfur has lost hydrogen, right? So we say it is oxidized, and chlorine has gained hydrogen, we say it is reduced. But these two definitions are not really very useful for deciding whether a particular chemical reaction is oxidation or reduction, mainly because this case is limited to hydrogen and oxygen only. So the current one that we are looking at is that oxidation is defined as the loss of electrons, and reduction is therefore the gain of electrons. Let's look at the following equation. So here we see Fe went to Fe 3 plus. So to balance this, I need to put electrons. I put 3 electrons here. So now you can see Fe has lost electrons. So this one is an oxidation. Next we see Cl2 goes to 2Cl minus. Sorry, 2Cl minus. Where do I put the electrons? I should put the electrons here. So it has gained electrons, therefore this is reduced. So this method actually accounts for all the previous cases as well. And this is actually the method we will use from now on. Now, in order to look at this equation and to decide what is oxidized or reduced, we need to write half equations. So what do we mean by half equation? It means half of an equation. So one half is the reduction, one half is the oxidation. So when you combine the reduction and oxidation, you should get the full reaction. Now this is a very important technique because this also allows us to balance the equation based on electron transfer. So let's look at this. Okay, so we have that. So we know Fe went to Fe3 plus. So to balance the equation, I need to put 3 electrons here. And after that, I know Cl2 goes to Cl minus, there's 2Cl, and then to balance the change in oxidation state, I put the electrons. Now, if iron requires 3, gives away 3 electrons, chlorine only accepts 2. So for them to combine, the number of electrons given and accepted must be exactly the same. So I make that to 6. I times the first one by 2 and times the next one by 3. And then I combine them together and I'll get the final equation. It is very important to note that this balancing of half equations is very important for redox type of reactions. Now why don't you try checkpoint 2.2 from your notebook. You should continue after you have finished. So in this case, we have Zn to Zn2 plus, so I balance with electrons. Sulfate to sulfate is the same. I have Cu2 plus going to Cu, so I balance with electrons. So these are the two half equations. So which have been oxidized? Zinc has lost electrons, so this is oxidized. And the second one, copper 2 plus has gained electron, this is a reduction. So when we write the half equation, we can actually explain oxidation and reduction in the terms of loss or gain of electrons. Now let's try checkpoint 2.3. Again, you should pause and continue only after you have finished. So in this case, we have Mg going to Mg2 plus. So I should put 2 electrons here. Then I've got O2 going to O2 minus. There's 2 of oxygen. So then I need to put the electrons. So the first case is lost electron. This is oxidation. Second case gain electron. This is reduction. And the third one is Ag plus. This is reduction. And Pb this is oxidation. Now let's find an easier way to do this. Another way we can do this is looking at oxidation states. Now, oxidation state or oxidation number is actually a hypothetical number and it's related to a charge. For example, Fe3 plus, the oxidation state equals plus 3. Cl minus, oxidation state minus 1. However, in some cases whereby you have covalent bonds like CO2, it is also possible to count the oxidation state. In this case, there are some assumptions. It is calculated based on a theoretically ionic world. And how we calculate for covalent, we will carry on in the next slide. So first of all, there are some rules. So the first rule is that the charge of the chemical entity is the summation of all the oxidation states. For example, like if I had FeCl2, right? Now the charge here is 0, so total oxidation state equals to 0. So Cl I know is minus, so Cl is minus 1 minus 1. So in this case, my Fe must be plus 2 because the total oxidation state at the end is 0. Okay, but however, if you have some elements like Br2, the oxidation state in this case is 0 because what times 2 equals 0? It must be 0. Now, to understand more, let's look at the following rules. Now, the rules in assigning oxidation states are as follows. I need you to memorize this in the sequence given here. So this is number 1, the most important, and to start first. Number 2, second one, third one, fourth, fifth, and sixth. Now you do not need to know the exceptions because the exceptions are actually because of the ones before it. To show you what I mean, we'll do some examples. Okay, let me show you for S8. So S8, the charge is 0, so 8 times what is 0? So the oxidation state equals to 0. Why? Because 8 times 0 is 0, which is the final charge. Now NO2, now in this case, the total oxidation state should be 0 as well. So we go on from the top. Is there a group 1 metal? No. Is there a group 2 metal? No. Is there F? No. Is there H? No. Is there O? Yes. So O is given minus 2. You have 2 O's, so minus 2. Now after that, now we only have nitrogen, which is left. Okay, so in this case, so nitrogen that's left plus this minus 4 must equal 0. So nitrogen's oxidation state in this case is plus 4. Now you try for KMnO4 and OF2 and then continue. KMnO4. The first thing we assign, K is plus 1. Then number 2 doesn't have, 3 don't have, 4 don't have, 5 have. So this is minus 2, minus 2, minus 2, minus 2. Total must equal to 0. So in this case, Mn must be plus 7. What about OF2? So you go from the top again, and in this case, F comes first, well, minus 1, minus 1. So we do not, the moment we have reached this case where there's one element left, you do not continue anymore. So you do a calculation equals 0. So in this case, oxygen is plus 2. Notice it is not assigned in this case to minus 2 because F is assigned first. So how can we use oxidation numbers of oxidation states to tell us whether a species is oxidized or reduced? Well, as you remember, loss electron oxidation, gain electron reduction. So if you lose an electron, oxidation state increases. So if the oxidation number of oxidation state increases, therefore it's an oxidation. For reduction, the oxidation state is reduced. Now let's try checkpoint 2.7. Identify the species that have been oxidized and reduced, and explain. You should pause here and continue after you have done this. So this case, H is plus 1 minus 1. This is still plus 1, so no change. but Cl has changed from -1 to 0. So -1 to 0 is oxidation. And then we see Mn is +4 -2 is +2. +2, +4 to +2, that's a reduction. But how are we going to write this out properly? So the first, we need to answer the first part, is identify the species. So we would say Cl minus has been oxidized as if oxidation state increases from -1 to 0. And then the next one, we will write Mn in MnO2. Notice this case, I don't say it's Mn4 plus because it's solid. So it doesn't really exist as 4 plus, and actually in this case, it also does not a 4 plus. So you just write Mn in MnO2 has been reduced as its oxidation state reduces from +4 to +2. Okay, and that's how we identify the species as well as explained based on oxidation state. Now for the second part of this course, we'll look at how to balance half equations. So half equations are also similar to other chemical equations in the sense that there's conservation of mass. So the number of atoms for each element on the left must equal to the number of atoms of that element on the right. And next, there must be balance of charge. So the summation of charge for the left-hand side and right-hand side must be the same. The unique thing about redox is that the oxidation states actually balance using electrons for the half equation. So we're going to go through two types. First is a simple one, which means the elements present on both sides of the half equation is exactly the same. The second one is more complicated because you can now have oxygen present on both sides, but they may not be of the same amount. We'll look at this later. So simple type is very simple. We write the elements present, we balance the elements, and then we balance the oxidation state by adding electrons. For example, Cl minus to Cl2. First stage, balance the elements. There's 2 Cl on the right, so there must be 2 Cl on the left. Next, to balance the oxidation state, this case I have to put 2 electrons here to balance. And then let's go to the next one. So complicated one. It's complicated because there's different amounts of oxygen. For example, if I have something like MnO4 minus to Mn2 plus. Now in this case, there's extra oxygen here. So how do we handle all this oxygen? We need to remember the water equations. So there are 4 water equations which I need you to remember. Okay, 2 of them is for the case whereby the left hand side has too few oxygen, and 2 is for the case on top where the left hand side actually has more oxygen than the left. Sorry, the left hand side has more oxygen than the right. So in this case, we need to balance using the two equations at the bottom. Yeah, sometimes when you go to the exam, you may forget. So how do you remember? Just remember there's a H2O to form 2H plus, H2O to form 2OH minus. Right? And then you flip it around, you have 2H plus, 2H2O, 2OH minus, 2H2O. Now, when to use this, you need to know whether the conditions around your reaction is acidic, basic, or neutral. For acidic, of course, acidic, you have H plus. Acidic, you have H plus. So you have two equations for acidic. You have two equations for basic. Now for neutral, the only difference is neutral must start with H2O. Because in a neutral condition, you don't have H plus and OH minus. So this one is for neutral and neutral. Now let's try the following. MnO4 minus to Mn2 plus. First we balance Mn. So it's 1 to 1. Okay, that's good enough. So then you have MnO4 minus. Next, we balance the oxidation state. Over here, minus 2, minus 2, minus 2, minus 2. So this one equals to minus 1. This one must be a plus 7. Over here is a plus 2. So plus 7 to plus 2, I need to add 5 electrons. Right? Next, I need to balance the equation in the correct medium. In this case, we are told it's acidic. So acidic, we have H2O, the 2H plus, and 2H plus, 2H2O. Now looking at this case, there's too many O's on the left. So I should choose the one which has more O's on the right to balance. How many O's I have? 4. So I need to add 4 times of this. So I have 8H plus and 4H2O. And that gives me the full equation. Thanks. How do we combine half equations? Well, we combine half equations noting that the number of electrons lost must equal to the number of electrons gained. So what's the general sequence? First of all, you determine the two half equations. Then you multiply the equations such that the number of electrons gained and lost is exactly the same. Let's look at how is this formed. Now let's look at, you are told Fe2 plus goes to Fe3 plus and MnO4 minus goes to Mn2 plus. So in the first case, it's quite simple. I need to put an electron. The second case, first of all, I balance Mn, 1 is to 1. Then balance oxidation state. It's plus 7, plus 2. So I put 5 electrons. It's acidic. So I have I'm going to use the second one. I need 4 of this. And that's balanced. Next, 5 electrons and 1 electron. So the first one I need to times by 5. Okay, so then I add it up together. I have 8H plus And that gives me the full equation. Now you try the following and pause this video, continue after you have finished. Well, for the first one, we already know it is okay. For the second one, I have SO3 2 minus going to SO4 2 minus. Minus 2 minus 2 minus 2 equals minus 2, so this is plus 4. This is plus 6. So I need to put 2 electrons here. Right? Next is acidic. I need to balance the equation. I can either use H2O to 2H plus, 2H plus to H2O. Now in this case, I have too many oxygens on the right. So I need to use the first one. I need one extra oxygen, so I just add one time. And that's the second half equation. Now how do I balance? I have 5 and I have 2. So the first part I need to times 2, second one I need to times 5. So I write the equation 2MnO4 minus plus 16H plus 5H2O plus 5SO3 2 minus 2Mn2 plus 8H2O plus let's see 5 SO3 2 minus plus 10H plus. And then I simplify 5, I make this to 3, this is 6, and this is cancelled off. So I have 2MnO4 minus plus 6H plus 5SO3 2 minus so 2Mn2 plus 3H2O plus 5SO, oh sorry, this is SO4 2 minus. Now let's try and combine what we know now with mole concept. So in this case, first thing we need to do is write the equation. So this one is the MnO4 minus plus 8H plus N2 plus. The second one is Fe2 plus to Fe3 plus. So I need to times this by 5. So I have MnO4 minus okay, so I'm told amount MnO4 minus equals volume times concentration, and that gives me mole. So amount Fe2 plus equals 5 times that equals So concentration Fe 2 plus, which is also concentration FeSO4, equals amount divided by volume. And that's the answer. Now let's look at this thing called oxidizing and reducing agent. So an oxidizing agent causes something else to be oxidized. So now remember we said if something is oxidized, the other thing must be reduced. So if an oxidizing agent causes something to oxidize, it itself must be reduced. Similarly, a reducing agent is a substance that causes another substance to be reduced. So in the process of causing something to be reduced, it should be oxidized. So how do we test for an oxidizing agent? We need to use a reducing agent. The most common one is an iodide. So the iodide goes to form iodine. So this is colorless, becomes brown. How do I test for a reducing agent? Well, I use an oxidizing agent. The most common one to use is potassium permanganate, potassium manganate 7. So it converts from manganate 7 to Mn2 plus. Okay, this is pink, goes to colorless. So all these tests, we use those that have color changes so that it's easy to see the change. So as summary, you have learned that redox reaction involves the movement of electrons. Reduction, electrons are gained. Oxidation, electrons are lost. So in reduction, since you gain electrons, therefore the oxidation state is reduced. In oxidation, since you lose electrons, the oxidation state is increased. You have learned how to count the oxidation state, so you can try for the following. What's the oxidation state of Cr in K2Cr2O7? So if you go down, it's plus 1, then minus 2, minus 2, minus 2, minus 2, minus 2, minus 2. Overall equals to 0. So this is plus 12, but there are 2 chromiums. So each chromium is plus 6. So the oxidation state of chromium in K2Cr2O7 is plus 6. What about Mn in MnO4 minus? So MnO4 minus equals minus 1 is plus 7. Now let's look at which one the oxidation state has been reduced. You should try it first and then we will continue. Minus 2 equals minus 2. This is plus 2 plus 2. Alright, this is minus 2, minus 2, minus 2, minus 2, minus 2. 1, 2, 3, 4, 5, 6, 2. So it's plus 10 divided by 4. So it's plus 2.5, plus 2.5, plus 2.5, plus 2.5. Okay, so this one, the oxidation state has increased. This one is oxidize. This is from 0 to -1. This is reduce. So what is reduced? Iodine is reduced. Its oxidation state has changed from 0 to -1. Okay, you try yourself for the following and then we will continue from here. Okay, so in this case I have Cr2O7, 2 minus, let's not put a K, Cr3 plus. First I balance the Cr, so I need 2 Cr3 plus. Next, this one should be -2, -2, -2. -2, so this is plus 12. There are two of them, plus 6, plus 6, plus 3, plus 3. So I need to put 6 electrons to balance that. Next, I need to balance in the basic condition, so H2O to 2OH minus, or 2OH minus to H2O. I notice my equation has too many O's on the left, so I need to use the one which has more oxygens on the right. I need 7 of it, so I have 7 H2O. And that's for the first one. For the second one, I've got I minus to I2. Balance the I. Balance electron. So now I have 2 electrons, 6 electrons. I need to times this by 3 and add together. Now I've gone through the whole steps with so many steps. I made a mistake. So how do I know? I check the total charge. Over here I have -2, -6, total is -8. Okay, over here I have +6, -14. That also gives me a -8. Notice these are exactly the same. Therefore, I'm quite confident I've done the correct working. And that brings us to the end of this course. Thank you.